Hi guys, this is a short video regarding section 4.2 in your text, and I've tried to label each definition and theorem with a page number in the name, or possibly theorem number, so that you can utilize your text and trace back what we're talking about with your printed material that you already have. So section 4.2 has got a lot of definitions in it and a lot of new vocabulary, and you need to get a handle on the vocabulary. The first definition that I want to point out is on page 200. It's those definitions of absolute maximum and minimum. And maxima and minima is the plural form of each of those two words. Extreme values are just maximums and minimums, but the actual way you pluralize extremum is a single one, extrema is the plural form. So extreme values on an interval, you get, you define this way. If f is a function on an interval and a is a value is an input that's in the interval, we say that f of a, notice f of a is the output, we say that f of a is the absolute minimum of the function on the given interval. If f evaluated at a is less than f of x for every single x in that interval. Makes sense. And then the absolute maximum of f on that interval is the output or the function value that exceeds f of x for every x in that interval. Exceeds or is equal to. Those are absolute extrema, absolute maximum and absolute minimum. The definition of the local version of extreme values, or extrema, is on page 201 in your text. Figure 3 on the next page, page 202, will help you build intuition about the difference between local extrema and absolute extrema. But let's draw a little image together that will kind of help us sort those two ideas out. So I'm just going to draw a funky looking random function. Okay. And you can see your eye is drawn to various portions of the graph when we're talking about extreme values. This guy right here is extreme. He's kind of the biggest, the highest point around. This guy right here is sort of the lowest point around. You're looking for the very tippy top of the peaks and the troughs of the very lowest part of the troughs or valleys. Now, if we assume that this function continues going down here, going up on the right, then this guy right here is just a local maximum, because there are, along the various x values in the domain, there are higher x values for which the function value is higher. Function values here are higher than the function value here. So this is just a local max, or local maximum. Here's another local maximum, because there are other function outputs that are higher than the function output here. And for the output I'm looking at here on the y-axis. This guy right here is a local minimum, because while this is the lowest point around, I can find an interval for which this output is the lowest output on that entire interval. There's other lower outputs than that, smaller outputs. This point right here is a local minimum and an absolute minimum. So I'll just abbreviate ABS. Whoops. Absolute min. Okay, so this one is the only one in this image that's a local min and an absolute min. The others are local extrema. Here we have a local max, here we have a local min, here we have a local max. And something to notice about all of these locations, and maybe your eye's already seen it, is the tangent line to the graph at those points. The tangent line to the graph at each of those points is horizontal. That is, all the extrema have a horizontal tangent line at those points. There's another place on the graph, though, of this funky function f, let's call it f. There's another place on the graph that has a horizontal tangent, and it's about right here. And notice there isn't an extrema there. That's not the highest point around, it's not the lowest point around. That is a place where the derivative is 0, where the slope of the tangent line is 0, and yet an extremum does not occur there. So just keep that in mind. The next definition that we need to discuss, again, this is so that we can have a common vocabulary. When in your exercises you see find the critical numbers or find the critical points for a given function, you know what that means. Here's the definition. It's on page 202, and I've got numbers in parentheses here because I sometimes say critical numbers instead of points, because even though it's called a point, it's not an ordered pair, it's just a number in the domain. So a critical point or number is a number C in the domain of a function if either the derivative is 0 at C or the derivative does not exist at C. That's what a critical point or a critical number is. You're looking for the values of the domain where the function's derivative evaluates to be 0 or the function's derivative does not exist. That's a critical point. So if you're looking just at this graph, even without having a rule for it, we can tell where the derivative is 0. The derivative is 0 here, and here, and here, and here, and here. All of those inputs, let's call this one C1, this one C2, this one C3, here C4, here C5, C1 through C5, all of those are critical numbers. They're inputs that make the derivative equal to 0. And this particular function doesn't seem to have any inputs that make the derivative not exist. This is a smooth differentiable function. Looks very like a polynomial. Okay, and the last theorem that we'll discuss in this video is theorem 2 on page 202. It's Fermat's theorem on local extrema. And what Fermat's theorem says is if f of c is a local max or a local min for a function, then that input is a critical point of the function f. Essentially, if you have a local max or a local min, then that c value, that input value, is a critical number for the function f. Local maxima and minima occur at critical numbers. Notice, however, not every critical number gives you a local max or min. However, if your function has local extrema, you can find them at critical numbers.